In this segment, we'll talk about the spectrogram, also known in some other programs as the density spectral array. But we'll start with the discussion of the frequency analysis, which is integral to understanding the spectrogram and other trends. So we'll talk about the technical details, the clinical application, and some examples. Now, the frequency-based trends include the spectrogram band power at power ratio and the spectral entropy. Essentially, all of the frequency-based trends are dependent on the Fourier transform. Fourier transform is a way of converting the time domain information, that's the raw EEG, into frequency domain information, which is the frequency spectra. If you look at the raw EEG is pretty polymorphic. It contains lots of different frequencies and lots of mixed frequencies. Just like white light contains light of all of the different wavelengths combined together, we use a prism to separate white light into its component wavelengths. And we use the same way the frequency spectra, the Fourier transform, to convert the EEG into its component frequencies. We can use our measurement tool to drag a box around the time segment. We generate an FFT frequency spectra that could be virtually any length of time. In the first example here, we're looking at about 2.5 seconds, but it could be 2 minutes, it could be pretty much anything, because what we're trying to do is represent the component frequencies. So we've selected a couple seconds here, and the component frequencies in this segment are predominated by 5 hertz and 3 hertz activity. And again, keep in mind that with these frequency spectra, our y-axis is power and our x-axis is frequency. So we're looking basically at 0 to 30 hertz. And the majority of the power is at 5 and 3 hertz. Now in the segment below, same EEG, we've selected a different channel. You can see in this channel the predominant frequencies are around 13 and 14 hertz. And of course this corresponds to sleep spindles, which we can pretty clearly see. Now when we do a frequency analysis for trending, we're simply doing serial FFTs and putting that data on a graph. Again, each epoch can be 2 seconds, or it can be longer, it can be 2 minutes, or any amount of time. We're simply converting information from the time domain into the frequency domain. All of the trends that I mentioned before use the Fourier transform as the basis for their analysis, and each one has a unique method of displaying the results. The spectrogram is one of the most often used. It may be called the DSA, or the density spectral array, in other programs, but it's composed of multiple frequency spectra. The spectrogram takes that frequency spectra and color codes each frequency segment based on the power of that frequency. It isn't really necessary to do this for a two-dimensional waveform, but if you want to use the frequency spectra to look at three-dimensional information, it's actually very useful. Now here's that frequency spectra that we looked at. And we can take each one of these frequency spectra, and essentially what we do is we flip them over, turn them around, and then stack them next to each other. In the spectrogram, our y-axis is frequency, our x-axis is time, and our z-axis is power, represented by the colors on the color scale. So we're going to do our one and only quiz here during this presentation. So this is a 30-minute recording. Again, the y-axis is frequency, the x-axis is time, and the z-axis, the colors, are power, according to the scale on the left. So what we see is that in the first 10 minutes of the record, the most predominant frequency is in the 8 to 12 hertz range, as indicated by the dark red in that early part of the trend. As we get to the next 10 minutes, we see this activity drop in and out, and you see the prevalence of slower activity in the alpha and delta ranges. And then in the last 5 minutes, you see the return of the 8 to 12 hertz activity. Now in describing this, I'm trying not to make it completely obvious, but this is a normal sleep recording during a routine EEG. So you have the initial wake portion with the majority of the activity in the alpha range. You have the alpha dropout as they drop off to sleep, and probably vertex waves, sleep spindles in there, and stage 2 sleep, and then the arousal, and they are awake for the remainder of the study. Now another thing that the spectrogram is useful for is identifying seizure activity. In this example below, you can see the cursor in the spectrogram is placed on a peak that corresponds to the seizure activity in the EEG. Now not all peaks in this trend correspond to seizure activity, so it's useful to understand which ones do and which ones don't, and why they do or don't. Now, before we get into that, let's talk a little bit about what you can change in the trends. In the spectrogram, you can adjust the frequency range. That's the scale, the 0 to 50 hertz scale. You can adjust the electrodes that you select, whether it's bipolar, referential, and which specific electrodes you choose, and of course the time scale. Now there's one thing that's a little bit different in the spectrogram as well. You see something called the frequency band. Now this really does not relate so much to the spectrogram as it does to a little white line that allows you to show the band power overlaid on the spectrogram. And I'll show you an example of that as well. So if you just want to look at the spectrogram, you can pretty much ignore this frequency band selection. Now this is the example. So in the analyzer settings, I set up my frequency band to be 2 to 4 hertz. And then in the band power trend analyzer, I've set up the same thing so that you can see a good example of exactly what we're seeing with that white line. It is exactly the same thing as the band power. It's simply overlaid on top of the spectrogram so that you can compare the two to each other. Now I have a couple of quick examples to show you. This first one is a normal EEG, so this is a 24-hour study, and we zeroed in on 4 hours, a 4-hour segment, just to point out a couple of things. So right now where my cursor is, you can see this little blip that's at about 9 to 10 hertz, and that corresponds with the alpha. Now, as the alpha drops out, you can see that's gone, a little bit of movement there, but you can see, if I click here, you can see this little blip that's at 14 hertz, and that of course corresponds to the sleep spindles. So you can very quickly identify where this patient is falling asleep by the sleep spindles. You can also very quickly identify where they're arousing by the alpha. So this gives you a very easy way to look at 4 hours of data and understand the state of the patient and what's going on here. Now there's some other waveforms here, some other frequency spectra here that are mostly artifact, and I suspect are mostly related to arousals. There we go. As you'll see in the next example, you can identify the difference between the arousals and seizure activity. So now this is a patient with generalized epilepsy. So this is a 30-minute recording. I've just zeroed in on a short segment of it so we can identify what's going on here. So you'll see several peaks in the trend, and you'll notice that they do look different. So of course we have this out here that's clearly artifactual, except for one peak within there where you see this striped waveform. And that's similar to the striping that you see here in this peak, and in this peak, and in this peak. Actually, there's a few other peaks as well. You notice it's not the same appearance that we see in some other peaks. For instance, this peak doesn't have that nice stripe, and that's artifact. So when we see that striping, at least for this patient, we can make a reasonably good judgment that there's seizure activity. You'll notice this striping in this activity is very much different than the appearance of these others. Now this may be an imperfect tool, but again, the intent of this is to draw your attention to specific segments, and it does that quite well. So again, to reiterate, trending, no single trend stands alone. You want to use multiple types, play one trend off the other, optimize your EEG by customizing it to your patient, because no one set of trends is perfect for everyone. And again, raw EEG, always the gold standard. Can't emphasize that enough. The intent of the trends is simply to draw your attention to the raw EEG.